In this video, let's go ahead and apply our understanding of ratios, rates, and proportions to 4 different application problems together. Alright, so let's get right into it. In number 1, we see that a movie is filmed so that the ratio of the length to the width of the image on the screen is going to be 1/8500ths to 1. Make sure we know the length goes first, and width goes second. So if we're going to be writing a ratio of length to width, let's just make sure we label everything really well here. So length is going to go on top of this fraction form, width is going to go on the bottom. So our length is going to go first. We're going to write 1/8500ths on top. We're going to go ahead and put this 1 on bottom, so we kind of have a unit ratio here. And they're saying, what if the width is going to be 38 feet here? So the width, they're saying, is going to be 38 feet. So where is that going to go? Well, let's keep things nice and consistent here. The width is going to go on the bottom. And then we're going to go ahead and write our unknown here for the top. If we don't know the top here, that's just going to be L, or you can use X or something like that. Now there's multiple ways of going about solving this proportion. We can just go ahead and use cross products if you would like to, or you can use equivalent ratios or use the identity property. But if you multiply the cross products here, we're going to find out that the length here, or 1L, is going to be equal to whatever the product of this 38 by 1/8500ths is. So we go ahead and write this out really clearly. It's going to be 38 multiplied by this 1/8500ths. So let's go ahead and just multiply those real quick and see what that's going to be. I'm going to go ahead and just take this 1/8500ths, and I'm going to ignore the decimals for a moment. We'll put the decimals back in once we need them. So that's going to be 40, carry the 4. That's 64, plus the 4 is 68, carry the 6 here. That's going to be 8 plus 6, that's 14. Let's put a placeholder here. Then we have 3 times 5 is 15, carry the 1. 24 plus 1 is 25, carry the 2. Then 3 plus 2 is going to be 5. So let's go ahead and add these two partial products up. We're going to get 0, 3, I think this is a 0, and I think a 7. Now we ignored 2 decimal places earlier, so let's go ahead and put a decimal back in that makes sense here. So 70.30 or 70 30 hundredths. We can go ahead and say maybe the length here is going to end up being 70 3/10 here. So we can go ahead and conclude that if the width is 38 feet, that the length must be 70 3/10 feet. Alright, for part B, let's go ahead and make a table that shows the length of the image when the width of the image is specifically 20, 25, 30, 35, and 40 feet. So these are a bunch of different widths that we're being asked to compare to. So let's go ahead and just make sure we understand what all these numbers are over here. And so let's go ahead and make a table. So we can set up a table that looks something like this, and then just fill in the widths that we were given of 20, 25, 30, 35, and 40 feet. So we have a bunch of widths here, and we can use our initial ratio of this 1.85 to 1 and just make a bunch of comparisons to figure out what each of these lengths would be here. So we have this 1.85 to 1 over here. For this first part, let's go ahead and say, well, if this is 20, what's this blank going to be up here? I'm just going to go ahead and say, well, if you could multiply 1 by 20 to get 20, then 1.85 times 20, we can figure out what that's going to be. And so if you go ahead and just do some multiplication here, we're going to see that when the width is 20, the length here is going to be 37. Then you could go ahead and do this again when the width here is going to be 25, right? So same idea here. You can use cross products if you'd like to, or you can just kind of say here that 1 times 25 is 25. So you can take this 1/8500ths and multiply this by 25, and that would work well as well. And so you can see that when the width is going to be 25, the length here is going to be 46 2500ths. So that we can go ahead and put into our table, or you could write a fraction if you would like to. Now what about when the width is going to be 30? Hopefully you're kind of getting the picture here, or seeing the pattern of what we're doing. Again, you could use cross products if you want to, or you can just go ahead and take this 1 multiplied by 30. So 1/8500ths times 30 would also get you what you're looking for. And so when the width is going to be 30, then our length here is going to be 55 5/10, or we can say 55 1/2. Next, what about when the width is going to be 35? The width is going to be 35 here. We can just go ahead and say 1 times 35 is 35. So 1/8500ths times 35 would get us the length that we're looking for here. So let's go ahead and take this 1/8500ths, or 185. Let's multiply by 35 and just put the decimal in where it belongs. All right, so it looks like when the width is going to be 35, the length is going to be 64 and 75 hundredths, or we can say it's going to be 64 and 3/4. Finally, for this last one, when the width is going to be 40, I'm going to use a slightly different method to kind of do this one. I'm noticing here, instead of going from this 1 and multiplying by 40 here, then multiplying this 1 at 85 hundredths by 40 as well, we can maybe just take this 20. If you take this 20 and you double it, that's going to be 40. So if you take 37 and you double it, I know 37 times 2 is going to be 74. So I'm just going to go ahead and say this is going to be 74, and then not actually do any of that standard algorithm business down there. I think it should be a little bit faster for me. So at this point, we filled in our table with a bunch of equivalent ratios from the length and width of this image at the movie theater maybe, or on the whatever screen that they're showing. But we're supposed to go ahead and show the reasonableness of our answer to part A. So remember in part A, we were talking about when the width was 38. And so 38 falls between 35 and 40 here. So we had gotten a length of 70 and 3/10. And you want to check to see, does that seem reasonable? Does it fall in between these values here as well? So maybe what we could just write more simplistically is that because 35 is smaller than 38, which is smaller than 40, right? Because 38 over here fits between these two values on a ratio table, then it kind of makes sense where our value lies between as well. That if you look at the length, that the 64 and 3/4 is indeed smaller than the 70 and 3/10. I'm just going to write fractions here to stay consistent, which is smaller than the 74 here. So the whole idea that you want to try to check for the reasonableness is that this 38 falls between these two widths here, and that makes sense proportionally because the length that goes with it falls proportionally between these two lengths over here. All right, let's check out number 2. All right, for number 2, one day the ratio of skiers to snowboarders on the mountain at a ski resort was 13 to 10. The resort sold a total of 253 lift tickets during the day. All right, so notice that the skiers goes first and the snowboarders happen to go second here in the problem. So let's just make sure we know which numbers are going with which ones here. And what's this first part saying? It says find the ratio of snowboarders. Now, and we're going to find the ratio of those snowboarders to what? It says to all the skiers and the snowboarders on the mountain. So we're not just finding ratio of snowboarders to skiers or anything like that. It's going to be snowboarders to everyone. So if there were going to be 10 snowboarders, then how many total people would there be? Well, 10 plus 13 is going to be 23 here. So that would be our ratio. So you could just write it like this in fraction form, or you could write it, if you wanted to, using a colon form or using the words. But this would be just a 10 to 23 ratio. All right, part B, it says to use the ratio from part A to find the number of lift tickets sold to snowboarders during the day. So if we set up this ratio of snowboarders to everybody, we kind of already have this ratio. We know it's going to be this 10 to 23. So we can go ahead and just set that up first here. And then it says how many tickets were sold. Well, we know that a total of this 253 lift tickets were sold. So if we go ahead and put that 253 on the bottom for all the tickets sold, we can go ahead and find out. Let's go put X here for the number that were belonging to the snowboarders. Now, up to you what kind of strategies you might want to use to go ahead and solve something like this. I'm going to go ahead and just use cross products here. I think that's typically a favorite method. So 23 times x is just going to be 23x. That's going to be one cross product. Our other cross product here is going to be 253 multiplied by 10. So I'm just going to go ahead and write this so it's super clear. Now 23x is just going to be 23x for a moment, but this 253 times 10 is going to be 2,530. And we can do is just go ahead and divide both sides by 23, and we'll find out what the value of X is, or the number of snowboard tickets being sold was. All right, so just doing a little bit of division there, we find out that X here is going to be equal to 110. And so we can conclude that 110 tickets were sold to the snowboarders if 253 tickets were sold during the day here. For part C, it says during the same day, the ratio of snowboarders who rented snowboards to the snowboarders that have their own snowboards is 4 to 7. It says find the number of snowboarders who rented a snowboard. So every 4 of the snowboarders who rented their snowboards, there were 7 snowboarders that just brought their own. So let's just go ahead and set up some sort of ratio table or fraction form of what's going on here. I'm basically setting up this fraction form of rent to own to total. And I'm going to go ahead and just write it like this, but feel free to write it in a table if you would like to instead. So for every 4 people that are renting, we know there are going to be 7 people that are owning. And I just want to make sure we understand that there are a total of 11 people in this scenario. Now, how many snowboarders were there on this day? Well, remember from part B that there were 110 people here that were snowboarders, right? So if we go ahead and put this 110 down here as the total number of people that were snowboarding, then what would kind of go in this table of our equivalent rates or ratios here. So well, you can see here that this is going to be 10 times more people here. So if you multiply everything by 10 here, then there must be 40 people that rented out of these snowboarders. And then 7 times 10, that's going to be 70 here. So there must be 70 of these people that owned their snowboards. So hopefully that makes sense when we have this 40 to 70 ratio that matches this 4 to 7. And so we can go ahead and conclude that 40 snowboarders must have rented. All right, let's check out number 3. In number 3, you and a friend are waiting in separate lines to purchase concert tickets. So that's kind of the scenario here. You and your friend are in 2 different lines. Let's check out part A. Every 10 minutes, the cashier at the head of your line helps 3 people. There are 11 people in line in front of you. Write a proportion that can be used to determine how long you have to wait to purchase tickets. So let's go ahead and set up a rate here of time to people. And so for every 10 minutes, we know 3 people are going to be helped here. So saying, what if there were 11 people that were in line in front of us? Let's go ahead and just say that 11 is going to be the number of people here. And we're going to put maybe X to represent how long it'll take that we have to wait here. So this would be a proportion that we could set up. All right, what about your friend here? We could essentially set up this same rate, except this time we know that your friend here says every 5 minutes they're able to help 2 people. So we have a slightly different rate here. And saying, what if there's 14 people in line ahead of your friend? Well, 14 is going to go on bottom where the people are. And then maybe we can go ahead and use Y to represent the amount of time that it's going to take for your friend to be able to get their tickets. Now for part C, let's go ahead and use what we found in part A and B to go ahead and make a comparison to see who's going to get their concert tickets first. All right, so let's just say this is going to be you. If we go ahead and maybe use cross products here, we can find out that x times 3 is going to be 3x, and then 10 times 11 is going to be 110. If you go ahead and divide both sides by 3 here, we should find out that x is going to be equal to 100 thirds. 100 over 3. Maybe as a mixed number here, this is going to be, I think, 30. That's going to be 9, and then I think it's going to be 36. And 2/3, so that's gonna be 36 minutes and maybe 40 seconds, right? So we could say that this would be 36 minutes and 40 seconds, because that's 2/3 of a minute. And then what about your friend? Well, for your friend, we can go ahead and solve this proportion here. We can use cross products too if you would like to, or if you'd like to, you can see that maybe 2 times 7 is 14, so 5 times 7 would get you there pretty quickly as well, but I'm just gonna go ahead and write the cross products anyway, but if you prefer that, then definitely go for it. That's probably how I would do it personally. You can go ahead and divide both sides by 2 here. I think it's just a little more writing doing this way, but you'll find out that Y would be 35, and that represents how long your friend took, so that's gonna be 35 minutes and 0 seconds here. So in conclusion, we can go ahead and say, so we can say that your friend will purchase tickets first, waiting 1 minute and 40 seconds less. All right, let's check out one more problem here. In number 4, a motorcycle is traveling 60 miles per hour and goes 25 miles further in the same amount of time as a car traveling 40 miles per hour. A formula that's going to be helpful for us to know is that distance is going to be equal to rate times time, or D is equal to RT. All right, so to start off in part A, it says write 2 equations that represent the relationship between the distance, rate, and time for each vehicle. All right, so for the motorcycle, we can go ahead and start with saying here that the distance is going to be equal to rate times time. So let's say the distance, well, I'm going to go ahead and call this distance of the motorcycle. I'll call this D1 here. This D1 is going to be the distance for the motorcycle, and that is going to be equal to rate times time. Well, what's the rate of the motorcycle? It's going to be 60 miles per hour. And what's the time for the motorcycle? Well, we don't know what that is just yet. So I'm going to just say 60 multiplied by T. As for the car, we don't know the distance it's going to be traveling, but it's going to be different than the distance of the motorcycle. So I'm going to go ahead and call that D2 for now. So we have 2 different distances. So if we use that variable D, maybe it's more clear to use these little subscripts here. And so this distance is going to be equal to this car's rate, which we know the car is going to be traveling 40 miles per hour. So 40 R times T. We're just going to go ahead and write T there. So while we just wrote two different equations that represent the relationship between distance, rate, and time for each of these vehicles, I think it's important to note how the distances are related between these two vehicles. And remember that the motorcycle is traveling 25 miles further than the car is. So I think it's fair to say that D1, or the distance of the motorcycle, will be equal to the distance of the car, which is D2 plus 25 more miles. That being said, if we wanted to go ahead and just rewrite this top equation, we could even make this a little bit more clear for the future part of this problem. We can go ahead and say that instead of writing D1 is equal to 60 plus T, we can actually just go ahead and say that D2 plus 25, which is the same thing as the distance 1, or the distance of the motorcycle, is going to be equal to 60 multiplied by T. So if we use this equation as the relationship between distance, rate, and time for the motorcycle, and this equation over here, notice that we have one less variable instead of having distance 1 and distance 2 and time, which is a total of 3 different variables. Now we just have 2 different variables where we have this distance 2, time, and time. So there's one less variable to deal with if we make that relationship. All right, let's check out part B. So since the vehicles traveled for the same amount of time, isolate the time variable and use substitution to set up a proportion. So this is our equation for the motorcycle, and it says to isolate this t variable since we are told that they are traveling for the same amount of time. We can do that by just dividing both sides by 60 over here. If we go ahead and do that, we find out that time is going to be equal to this d2 plus 25 all over 60. Okay, so that's going to be for our time isolating for the motorcycle. Now here is our equation for our car, and to isolate the time here, we can go ahead and divide both sides by 40. If we go ahead and do that, we can see here that this time would be equal to distance 2, or d2, divided by 40. All right, cool. Now we know that the time is the same for both vehicles. We were told that information, so this t over here must be equal to this t over here. And in turn, we should be able to say then that this expression over here is equal to this expression over here. So what is this proportion that we can set up here? We can go ahead and say that this d2, or the distance of our car, plus 25 divided by 60 is going to be equal to the distance of, again, that car divided by 40. Again, this is really telling us the distance of the motorcycle, but remember the motorcycle is 25 miles further than the distance of the car, so we can set it up just like this. So here we isolated time for each of these equations, and here we wrote our proportion. All right, cool. Let's go ahead and try part C, where we're going to go ahead and find the distance of each of these vehicles. So we had set up this proportion just a moment ago. We can go ahead and solve this using cross products here. So if we go ahead and do so, our first cross product here is going to be d2 multiplied by 60. Or we can go ahead and say this is going to be 60 d2. And for our other cross product, we're going to have 40 multiplied by d2 plus 25. All right. If we go ahead and just use the distributive property here on the right side of the equation, we're going to find out that 60 multiplied by distance 2 is going to be equal to 40 distance 2, or 40 times d2, plus 1,000. If you go ahead and take away 40 d2 from both sides, we're going to get 20 d2 is going to be equal to 1,000. And if we divide both sides by 20, we're going to find out that d2 is going to be 50. So remember from earlier that d2 represents the distance of the car. And so if we go ahead and want to find out the distance of the motorcycle, that is going to be whatever distance 2 is plus 25. So if we go ahead and just write down that equation, that distance 1, or the distance of the motorcycle, is going to be whatever the distance of the car is plus 25. Then we can say that distance 1, or the distance of the motorcycle, is going to be 50 plus 25. So we know the distance of this motorcycle is going to be 75. And so we know the motorcycle is going to travel a total of 75 miles, and that the car is going to be traveling 50 miles, which are 25 miles difference as we expected. These would be the two different distances that the motorcycle and the car traveled. All right, finally for part D, let's go ahead and find out the amount of time both vehicles traveled for. And so this was our time equation for the motorcycle, and we actually know what this d2 represents now. So we can figure out the time here. So d2 we knew was equal to 50. So if we have 50 plus 25, we substitute in, divided by 60, then this would end up being 75 over 60, which we knew that was going to be the distance over that rate there. And in 75 divided by 60, we can divide those both by 15. That would be 5 over 4, which is basically what? That's going to just be 1 1/4. So that's going to be 1 hour and 15 minutes. Now just to confirm for our car equation is T is equal to D2 over 40. Again, we found out D2 was 50, so that's going to be 50 over 40. This should be the same, right? So 50 over 40 simplifies down to just being 5 over 4 as well, which is going to be 1 1/4. And so in conclusion, we can say that the time traveled for the car and the motorcycle was both going to be 1 hour and 15 minutes. All right, so there you have 4 different practice problems dealing with setting up some rates and ratios and proportions. If you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing.